Hello, welcome to ISAT 211. This is lecture 7, process flow design and analysis. So today I want to talk about mostly cycle time analysis. And this is a very important component in manufacturing management, because we need to understand how we can reduce the waste. And first of all, we need to understand what is the cycle time and also what are the production rates. First, the cycle time is the time between two successive deliveries. What does it mean is, for example, there's a whole production line that you can wait at end of the process, which is, let's say the door, the door of going out of the factory. And then you start to count, right? How often can you see a completed car can be made? So that is the cycle time of the factory. It's two successive deliveries. It's not about all the task time added up together. That's not cycle time. Right? Cycle time is how often one part or one product can be made. Right? So this cycle time. Another concept is takt time. So takt time is the maximum acceptable time to meet the demands of the customer. And so the takt time is basically to describe that how much time actually is available and what is the time you can give the factory to make the products. And a takt time equals to night time available for production divided by the customer's daily demand or customer's demand. Okay. So using this equation, you can calculate, for every day or for a certain time unit, and how many can need to be made. It does not mean that for during this time your order or this customer's order is everything they are making in the factory. But no, that's not the case, because the factory can process multiple orders at the same time during a period of time. For example, during today, I'm making not only a customer A's order, I can also make customer B, customer C, customer D's order. And in this case, as long as I can fulfill customer A's order in, within his or her request, then I'm good. So that's called takt time, right? So it means if I for example, if I order 20 products and I need it to be delivered by end of this week, well, the factory can actually make the 20 products in one day, but because you give the factory a whole week to make it, so which means that 20 divided by 5, you only need to make 4, right, each day for this customer. And that is a takt time. Okay, so just make sure that you understand this this term, takt time. And the lead time is a time from request to delivery. I think it's very easy to understand. Time from request means when do you place your order, and delivery is when you receive this order. So that's the lead time. And the work content time, that is a sum of cycle times of all processes to make a product or component. So you need to make a clear distinction between work content time and cycle time. Cycle time means how often can you make one product, right? And the work content time is at the time, all the necessary steps, all the necessary tasks times added up all together to finish one product, right? So this is the work content time. For example, if I have a product that it need 100 processes, right? 100 processes, and each process may take about 20 minutes. Means how many? What is the work content time? That is 100 times 20, because you need to add all these process times together in order to finish this product, which means that this product includes all these task times, right? So that is the work content time. And we can look at one example here to help you understand all these concepts. say a customer, just place an order of 75 airplanes and need to get them 2 hours later. Assume it takes about 10 minutes to process the order before putting an order on the production line. It takes another 10 minutes to deliver to the customer's address. The 75 airplanes were actually delivered 60 minutes after the order request. So which means that within an hour, all these paper airplanes actually delivered. Now, using this example, let's look at all these terms. First, what is the task time, right? So task time means the net time available for production. Now let's look at, okay, what is the time available for production? So which means that, okay, time available production is 2 hours, right? 2 hours, that is 120 minutes, 2 hours time, divided by customer's demand, all right? Customer demand is 75. So which means that as long as the factory can make 75 paper airplanes during the 2 hours, we're good, all right? So that is a task time, which means that 1.6 minutes per airplane, right? So this is a task time. This is what the customer gives the factory to do, all right? Well, actually, the order was delivered 60 minutes earlier, so which means only take 60 minutes, right? Half of the time to finish everything. So the lead time is order delivered minus order placed, right? So order placed at time 0, while the order delivered after 60 minutes. So which means that the lead time is actually 60 minutes for this order, okay? And this is a concept. All right, now let's look at another concept, which is work content time. So what is the work content time? So work content time means it's all the times added up all together. Oh, sorry, I need to make a little bit change here. So this is supposed to be 6, and this is the 8, and 5 and 7. 7, 26 seconds, okay? All right. Now, let's look at all the steps to make a product, right? The product requires that 1, 2, 3, 4 steps, and the parentheses or this row means that is the processing time. So to finish each task, how long does it takes, right? Step 1, it takes about 6 seconds. Step 2 takes about 8 seconds. Step 3 takes 5 seconds, and step 4, 7 seconds. These times are the times that is required to complete each task. All right, so the work content time means we're gonna add all these task times together, right? All the processing times together means 6 plus 8 plus 5 plus 7 equals 26 seconds, right? Suppose we are making a paper airplane itself. All right, we have 4 steps, and in order to make one paper airplane, you have to go through all these 4 steps, right? Otherwise, you cannot make a complete product. So this is the work content time. Now let's look at the cycle time. What is cycle time? Remember, cycle time is how often can you make one product. So be clear about this. How often can you make this product? Now let's look at this process. How often can we make one product? Think about this question. How often can we make one product? Is it 26 seconds? No, because all these process times actually can do it simultaneously, right? All these tasks can be conducted simultaneously at the same time. So which means that if you wait here, right? If you wait here at the end of process 4, which means about every 7 seconds, right? 7 seconds or 8 seconds, you can what? You can receive a new complete product. Isn't it right? Right? Think about the finish that time. Process 1 is doing task 1, 6 seconds. Process 2 is also doing his work. Process 3, same thing. Process 4, as long as there's a flow of products or the products keep flowing from on this line, which means that for process 4, the operator just keep working on his work, right? On the parts. So after 7 seconds, okay, I got a new part, and then I finish another last step, and then get a complete product. Then after I finish this, I get a new part, and then I use another 7 seconds, and then finish the product, and then get a complete product. So every 7 seconds, he finishes product. All right. So which means that how often can we get a complete paper airplane? 26 seconds. So this is a cycle time. This is the cycle time. Well, sometimes we can think about it. Sorry. So how often can we get a complete product? It's about 7 seconds, right? So this is what happens. This is a cycle time. Well, there's another concept. It's called repositioning time, right? Repositioning time. Repositioning time is the time from finish of the prior operation to being ready for the next operation. So the repositioning time is to describe that other than the operation itself, there's also a time to get ready for the next process. For example, you probably need to do some setups, or probably you have to transfer from your station to another station of your finished product. So which means that there is a small amount of time that required to get ready for the next operation, and the cycle time equals to both the process time, or here we also can call it service time, plus repositioning time. Think if it is the case, right? If you're an operator and when you receive a part and you start to work on it, and then after you work on it, you finish it, and then you put the part somewhere. Well, during the time of put the part somewhere, and then get ready for the next process, there is some time, right? So before you start your next operation, there's also a little bit amount of time. That is the repositioning time. So the cycle time equals to the service time of processing time plus repositioning time. Now let's look at, okay, for step 2, what is the cycle time? Assume that repositioning time for this step 2 is actually 1 second. All right. So it means that the cycle time for step 2 will be 8 seconds, which is completing the task itself, right? And also 1 second, to get it ready for the next task, right? So this is a cycle time. Let's be clear about these concepts. And the next concept is the line balancing. As you can see, for these 4 processes, process 1 takes about 6 seconds, process 2, 8 seconds, process 3, 5, and process 4, 7. And they are all not the same amount of time. So which means that, say, process 1, it only takes about 6 seconds to finish its part. And then after 6 or 7 seconds, we say there's a repositioning time. Okay, there will be a part here, but what happens with 2 is 2 has not finished yet. 2 has not finished the prior task yet because it takes about 8 seconds to finish its part, right? So which means there will be 2 seconds of waiting time here, right? 2 seconds of waiting time here. And then with time keep going on, and what happens is the waiting of the part will keep piling, go on, start to pile. And well, for step 3, what happens is for it takes about for step 2, it takes about 8 seconds. For step 3, only takes about 5 seconds. So which means that every time step 3 start to work on the part, it only 5 seconds, he's done. Then for 3 seconds, he cannot get the next part from 2 because 2 has not finished yet, right? So there will be a lot of waiting here for step 3, right? For step 3. And here, there's a lot of pile. Here, a lot of waiting. Same thing, happens with 4. Because 4 takes a longer time, there will be a pile of parts here, right? Now, this is what happened with, with all these processes, that they are not having the equal amount of task time or processing times. And this phenomenon, this situation, we call it, this line is not balanced, right? It's not balanced. And there we can calculate the line balancing efficiency using what? Using all the processing times added up all together. Remember, it's only the processing time, does not include the positioning time, right? Repositioning time. Only the process time, not including a repositioning time. So it's a 6 seconds plus 8 plus 5 plus 7 divided by what? Divided by assume all the processes are having this equal amount of processing time. And that time is the largest of all these processes. Which one has the largest or longest process time? Number 2, 8 seconds, right? So now let's assume all these processes, they all have 8 seconds. So that will be 8 plus 8 plus 8 plus 8. So 4 times 8, right? 4 times 8. These are the actual, these are the assume, all have the same equal amount of time. And then we get a percentage, right? That is 81.22%. And this efficiency, we call it line balancing efficiency, right? Now let's assume all these process time are actually the same, right? This is 8, this is 8, this is 8, this is 8, right? Then what is the line balancing? There will be 1, because they already, the actual process are already at 8 seconds, and then divided by n times longest service time is also 4 times 8. Then we got 100%. So which means if they are all the same, then that's 100%. If they're not the same, there will be an efficiency percentage here. Okay, so this is called line balancing efficiency. Well, now let's look at how can we determine number of steps of workstations given a task or given a product. So now let's assume we are making what? We are making something, right? Maybe it can be a paper airplane, it can be a computer, or it can be a car, right? Let's assume that all these steps added up together, we get a work counting time, right? We got a work counting time. Assume that work counting time is this amount of time, and then how do we know how many stations do we need, right? How do we know how many stations do we need? Well, first of all, we need to know that what is the cycle time, right? What is the cycle time? Think about this case. If we only have 1 station, what is the cycle time for making a product? Of course, that will be equal to the work counting time, because there's only 1 station, and all that station have to complete all the tasks by himself, right? So that is then that's how many stations do you need? Only 1 station if your cycle time is the same as your work counting time. But if you want to reduce the cycle time, right? Reduce the cycle time to a certain value, then we can calculate how many stations we need. Because the more stations we have, actually the smaller cycle time we can get. Okay, so now let's assume that we want a cycle time of 7, right? We want a cycle time of 7, and also we know the line balancing is 81.22, right? Assume that line balancing is this value. Now let's calculate how many workstations. Here we got 3.956, which is equal to close to 4. So which means that suppose that this is all the task time we need to complete the product. All right, we know the cycle time we want. And also we know the line balancing efficiency. Why do we need this line balancing efficiency? Because, right? Because here we are, if we only divide it by 7, now we assume that each process have the same amount of cycle time, right? But do they really have the same amount of cycle time? No, most time it's not. So there is a line balancing efficiency, right? So we need to multiply 81.25% to get the number of workstations. Okay. So this is how we calculate the number of workstations by giving a total work counting time and also a cycle time. Now let's say, okay, what about if we want to reduce the cycle time from 7 to 3, right? From 7 to 3. Now you can use the same value with the line, with the same line balancing efficiency, change this 7 to 3. Now you can calculate a new number, and either that new number will be a new number of workstations. So which means that you need to add more workstations in order to achieve a reduced cycle time. Okay, so this is how you can determine the number of workstations. Now let's look at another concept which is called production rate. So production rate means number of goods or products can be made, right, during a given period of time. Now let's assume that a factory starts to work at 9 o'clock and then finish everything at 5 p.m. right? 9 a.m. to 5 p.m. is very typical 8 hours working time, right, during the day. But what happens is during those 8 hours, it's not always, right? It's not always work. The production line is not always running. It's because there will be 1 hour of lunchtime, right? According to OSHA, according to common sense, right? We need to give the workers or operators some rest time or for lunchtime during the hours. All right, so assume there will be 1 hour of lunchtime, and also for during the morning shift and also the afternoon shift, that will be some rests, right? 15 minutes, let's say 15 minutes of rest. So 15 minutes of rest for during the morning shift and afternoon shifts. So two rests in the morning and 3 rests in the afternoon. All right. Now, because we know that during all these 8 hours and not always working, and we are paying, right? We have 8 hours of working hours. So there is a line efficiency, right? There's a line efficiency to use production time divided by total working time. What is the production time? A real production time is a green, right? Those green slots. These are production time. That is divided by the total working time. So you can get the line efficiency. And see what value can we get? Total working time will be 8 hours, right? 8 hours minus 75 minutes. 75 minutes, that means 15 times 5, because there are 5 rests, right? 15 times 5. Minus 60 minutes, that is a lunch break, right? So this is how we get. We calculate this number divided by, this is a actual production time, divided by total working hours at 8 hours. Then we get 71.9%. So this is a line efficiency. Well, there's another way to calculate the line efficiency, which is to use the cycle time divided by production time per unit. Think about the case. Cycle time means what? Cycle time means how often can I make one product, right, or finish one process, and the unit of cycle time will be time per unit, right? Time per unit, right? If we use 1 divided by cycle time, what do we get? We get unit per time, so, right? Unit per time. So which means that is, you know, during a certain time, how many units can be made, right? All right. So using the cycle time divided by production time per unit, here we can also calculate a rate. So that is line efficiency as well, because production time per unit means what? Means A accounts, right? A accounts all the what? All the rest and also working times, right? Production time per unit. But this variable includes all the rests, right? And lunch times together. So cycle time divided by production time per unit means we got our efficiency, means that, okay, that is the line efficiency, which is the same as 71.9%, right? Otherwise, what happens? Otherwise, you know, if say the line efficiency is 100%, which means that we're always making making products according to cycle time. But in fact, not the same, not the case, because there will be lunch breaks that the production line is not working, right? So we cannot just assume it is 100%. All right. So this is how we can use 2 different ways to calculate the line efficiency. And well, the variable production rate equals to a number of units produced divided by total working time. So this is the production per unit, right? For example, that here we assume that the cycle time is 1.5 minutes per product. What is our production rate here? And then this variable also equals to 1 divided by cycle time, because 1 divided by cycle time, we get what? We get how many products, number per product can be produced. Assume what? Per unit, assume the production line is always working, right? So this equals to the number of products can be made, assume the product, the production is always working. But is that the case? Not the case. So that we have to times this line efficiency, right? This is how we get production rate. All right, now let's look at example that assume the cycle time is 1.5 minutes per product. What is production rate? And then we can see, okay, during those 345 minutes, so 345 minutes is actual production time, those green slots, right? Added up together. This is 345 minutes production time, and divided by what? Divided by the cycle time. Divided by cycle time, we get what? We get, okay, 230 units can be made in 8 hours, right? Can be made in 8 hours. Because this is what? This is the time, this is the actual time divided by the cycle time. We know that how many units can be made. Well, what about production rate? Production rate is not the case, because production rate, we have to consider the efficiency, right? When we are looking at production rate, we're actually counting all 8 hours. If we are looking at, you know, how many can be made, you know, according to cycle time, we are only considering the green times, right? So the production rate equals to RP equals to what? 230 units divided by 480 minutes, right? 480 minutes. And why do we use 480 minutes? Because this is the total working time, right? Now we are using this equation to calculate it, right? 230 can be made, 280 working hours or working time. So we got 0.48, right? 0.48 unit per minute. Well, there's another way to calculate it, which is use this equation as 1 divided by the cycle time times what? Times the line efficiency, we get the same value. So this is the two different ways you can actually calculate the production rate. All right, now let's look at one example. To use an example, help us better understand the concepts. Say a manual assembly line is being planned for a product whose annual demand is 90,000 units, and a continuously moving conveyor will be used with work units attached. The work counting time is 55 minutes. The line will run 15 weeks per year, 5 shifts per week, and 8 hours per shift. And each work will be assigned to a separate workstation. So which means that for each work, each task or each worker only operates one workstation. And based on the previous experience, assume line efficiency is 0.95. We already have line efficiency. All right. Balancing efficiency is 0.9793, and the repositioning time is 9 seconds. Now it asks us to calculate the hourly production rate to meet the demand. Second is the number of workers and also workstations are required. First, let's look at the question A. What is hourly production rate to meet demand? All right, so in order for us to calculate the production rate, we know that, okay, let's see this equation here. If you want to calculate production rate, we either use this equation or use this equation, right? Let's see if can we use this equation, number of units produced divided by total working time. Do we know how many can be produced? For total work time? Yes, we already know that. Okay, annual demand is 90,000 units, right? It's 90,000 units. So this is the total amount, number of products to be made. What about the second one is total working time? Can we calculate total working time? Yes, because it already says that the line will run 50 weeks per year, 5 shifts per week, and 8 hours per shift. Now we can calculate how many total hours actually working hours during the year. Total demand of the year divided by total working hours of the year, then we can calculate the production rate, right? It's pretty straightforward to calculate this, right? Now, if you look at the equation, this is how we calculate the production rate, right? All right, our second question is to calculate the number of workers and workstations required, because each worker will be assigned to a separate workstation, which means that number of workers equals to the number of workstations. As long as you can calculate the number of workstations, then we are good. Then how do we calculate the number of workstations? We can use this equation, right? This equation equals to what? Equals to TC, so which is the total working counting time divided by the longest service time times the line balancing efficiency, right? Line balancing efficiency. Okay. Now let's go back to the description here. Total working counting time. Now we have work counting time, and we also have line balancing efficiency. So which means that as long as if I can find the longest service time or processing time, then I can calculate the total work counting, the total number of workstations. Now the job is to find out what is, right? The job is to find out, okay, what is the longest service time, right? Or processing time. Well, we have another equation, which is to which one? Is cycle time equals to what? Equals to the longest service time plus reposition time, right? So as long as I can find the what? As long as I can find this cycle time, because we already know the repositioning time, right? As long as I can find the cycle time, I can actually calculate this service time, longest service time. So the question becomes, how can we find out the cycle time, right? See, the repositioning time is already given. And we just need to find out the longest service time. Longest service time equals to this, right? And in order for us to find out the longest service time, we first need to know the cycle time. How can we find cycle time? Because we already know the production rate, right? We already know the production rate. And we can use this equation, right? We know the production rate, we know the line efficiency, then we can calculate the cycle time. So this is how we start with calculating the cycle time, right? You first equals to what this is the line efficiency, right? Line efficiency. We also have the production rate. We can calculate the cycle time because cycle time equals to repositioning time plus the longest service time. Then longest service time equals to the cycle time minus repositioning time. Then we get longest service time. All right, we have the longest service time. We have line balancing efficiency. We also have total working content time. We can calculate how many workstations, right? How many workstations? This is this number. So basically, we need 53 workstations, which means that we also need 53 workers. So this is how we can use cycle time for process analysis and planning. The most important part is to understand all these concepts. What do they mean? Then you can do a simple cycle time analysis. And that's all for this lecture.